Smaller than the United States by up to 235 times, the Netherlands has shattered seemingly impossible limits to secure the position of the world's second-largest agricultural exporter, directly competing with formidable rivals whose land areas are hundreds of times larger. How can a country with such a modest size, where more than a quarter of its territory lies below sea level, become one of the strongest agricultural economies in Europe, even leading outright when measured by export value? In this video, let's join Agriculture Insight to explore the agricultural ingenuity of the Dutch, where farming not only sets records in productivity, but also defines standards for low-emission agriculture, producing more while using less water, less energy, and less labor. All of this will be revealed right now. Most agricultural powerhouses possess at least one of two fundamental advantages: vast land area or a favorable climate. But for the Netherlands, their starting point consisted largely of land lying below sea level. Without expansive alluvial plains like those of France or Germany, most of their territory is made up of polders, artificial lands sustained by dike systems and pumps operating 24/7. Here, agricultural production constantly confronts saltwater intrusion, high humidity, and a lack of natural sunlight. It was precisely these harsh physical constraints that forced the Netherlands to choose a different strategy. Instead of expanding agriculture horizontally, like the United States or Russia, they focused on optimizing value density per unit of land area. At this point, every scarce square meter had to operate at extreme intensity, and even be completely detached from the soil. All of the most remarkable agricultural achievements begin with seeds. And in the Netherlands, more than 200 breeding companies have transformed the country into the world's leading hub of seed technology. Here, seeds are not developed for mass production, but are engineered as a core technical component specifically for smart greenhouses. They possess inherent disease resistance and respond precisely to every milligram of nutrients in a controlled cultivation environment. If the United States has Silicon Valley for software, then the Netherlands has Seed Valley, a hub that brings together more than 40 seed corporations, closely connected with Wageningen University and the government, enabling new plant varieties to move from the laboratory to global production in just a few years. You may be astonished to learn that 1 kilogram of specialized tomato seeds here can cost up to 50,000 USDs, as expensive as pure gold. This extraordinary price reflects billions of dollars invested in genetic research, allowing crops to achieve maximum yields while maintaining strong resilience without the need for chemical plant protection products. With this capability, the Netherlands now controls 25% of the global vegetable export value and 60% of the global seed potato market. From the United States to China, many of the world's leading agricultural systems are directly dependent on plant varieties originating from this low-lying land. Alongside seeds worth billions of dollars, another revolution in cultivation environments was pioneered, standardized, and spread worldwide by the Netherlands: rockwool growing media. At first glance, they appear to be nothing more than soft, lifeless foam blocks. But rockwool is in fact a complete replacement for the role of soil, a survival breakthrough for countries where arable land is always a luxury. The foundation of this technology comes from basalt rock and ores melted at 2,700 degrees Fahrenheit. From this glowing stream of molten material, the lava is spun centrifugally into ultra-fine mineral fibers and compressed into solid blocks. Thanks to its volcanic mineral origin, its superiority lies in its chemical inertness and absolute sterility, creating an almost perfectly clean biological growing medium that completely eliminates pathogens and prevents the nutrient losses commonly seen in traditional soil-based cultivation. Complete separation from soil gives Dutch engineers ultimate control. They precisely program nutrient concentrations and pH levels down to the milligram, delivering them directly to the root system without any interference or loss caused by impurities or unwanted absorption. From there, rockwool's fiber structure creates an ideal paradox for plants. It can retain water many times its own weight while still maintaining ultra-fine air pockets. This ensures roots are constantly supplied with maximum oxygen, completely eliminating the risk of waterlogging and common root diseases. Today, this technology covers more than 80% of greenhouse area in the Netherlands. Each growing block is a critical node in a closed-loop circulation system, directly connected to a central computer. The result is astonishing efficiency, up to 90% water savings and 40% fertilizer savings. And it doesn't stop there. All excess water is collected, sterilized, and reused, turning greenhouses into a sustainable production cycle that achieves the highest yields on the planet. When the Netherlands is mentioned, the whole world immediately thinks of vibrant tulip fields. But on the agricultural map, this is not a center for commercial flower production. It is home to the world's largest tulip bulb production facilities, supplying up to 2.5 billion bulbs globally each year. These bulbs form the foundation of the entire global flower supply chain, especially for massive markets such as the United States. However, to maintain this record-breaking position, Dutch farmers must carry out a decisive process, completely removing the flowers at their peak bloom. A tulip bulb requires 5 to 7 years of care before it is able to bloom. But the moment the petals reach peak color maturity, specialized flower removal machines are deployed immediately to redirect the plant's nutrient flow. Designed with rotating shafts integrated with rubber paddles and cutting blades, the core mechanism of these machines focuses force on the plant's weakest point, just beneath the flower head. As the machine moves forward, the high-speed rotating shaft snaps or cleanly cuts off the flower head without damaging the leaves or stem. Removing the flower head immediately halts seed formation and energy consumption at the top of the plant. This forces all sugars and minerals produced through photosynthesis to be redirected downward, concentrating nourishment into the bulb. By summer, when the leaves have withered, about 2 months after the flowers are removed, the true industrial harvesting process begins. Steel cutting systems lift the entire soil layer at a depth of around 20 centimeters, feeding it onto vibrating conveyor belts that sift and separate the bulbs on site, processing hectares of land each day. The breakthrough lies in crop protection. Despite being industrial machinery, all conveyors are lined with rubber padding and use high-pressure air-blowing systems to protect the thin, sensitive outer skin. This airflow not only removes dirt and fine sand, but also ensures the bulbs are not scratched, crucial for preventing bacterial infiltration during export. As a result, Dutch tulip bulbs grow to 10 to 12 centimeters in size, the gold standard for replanting in the world's most demanding markets. But make no mistake, beyond its empire of bulb production in open fields, the Netherlands still maintains a leading position in professional cut flower production within high-tech greenhouses. After being harvested by automated conveyor systems, millions of flower stems are consolidated and transported to Royal Flora Holland, the largest flower auction in the world. Transportation operates continuously via electric carts moving through an extensive system of sorting warehouses. Each day, this exchange offers up to 20,000 different types of flowers and ornamental plants. For tulips alone, prices fluctuate by the second and by season, but are typically successfully auctioned at an average range of US$0.22 to €0.55 per stem. While other countries require several days for transshipment, the Dutch reverse auction model delivers absolute price transparency and extremely fast capital turnover. Although the Netherlands is not the world's largest consumer market for fresh flowers, it functions as the brain that regulates global supply, allowing tulip shipments leaving the auction floor to land in the United States or Japan within just 24 hours after a deal is closed. With only 1.5 million cows, just 1/6 the scale of California, the Netherlands still amazes the world with record-breaking productivity. More than 9,000 kilograms of milk per cow per year. Each cow is a data node within a farm-wide IoT network. Through smart chips, the system can analyze and predict health risks up to 48 hours before clinical symptoms appear. This level of precision eliminates nearly all random variables, turning farms into an ideally optimized ecosystem. But in the Netherlands, technology doesn't exist only on charts. It takes physical form through tireless field operating machines, Lely robots. In reality, the number of farms in the Netherlands is declining by nearly 3% each year due to environmental pressure and a lack of successors, yet herd sizes continue to grow. Faced with this challenge, an automation revolution became inevitable, and at its center is the Lely Vector robot. Its crane system uses sensors to locate and precisely grasp roughage with a deviation of less than 2%. Immediately afterward, automated pipelines inject exact amounts of concentrated feed, which are mixed by an auger into a uniform blend, ensuring cows absorb nutrients completely and eliminating selective feeding. After mixing, the robot autonomously navigates through the farm to distribute feed. Its smartest feature lies in the ultrasonic sensors. The system measures the height of leftover feed and dispenses more only when necessary, ensuring troughs remain full while maintaining freshness 24/7. Notably, a single system consumes only about 20 kilowatt-hours per day to care for hundreds of cows. This quiet operation, with extremely low energy use, not only replaces human labor, but also creates a perfectly calm environment, key to keeping cows relaxed, maximizing oxytocin release, and sustaining peak milk productivity. To maintain high productivity, every cow needs a continuous energy intake. However, cows tend to use their noses to push feed sideways and out of reach, causing feed to scatter and go to waste. Lely Juno is designed to solve this problem. The robot operates as an automated system that moves along feed alleys 24/7, gathering and pushing feed back toward the fence. Keeping feed constantly within reach not only minimizes waste, but also stimulates cows' natural feeding behavior. Real-world results show that Lely Juno increases dry matter intake by 3%, equivalent to nearly 1 additional kilogram of milk per cow per day, simply by optimizing how feed is delivered. In the past, milking was the most exhausting burden for farmers. They had to wake up at 4 to 5 a.m., manually operating equipment for hundreds of cows on a forced schedule. This process not only drained human energy, but also placed significant stress on the herd. The Lely astronaut robot completely changed the game with a voluntary principle. Cows independently choose to be milked whenever they want, averaging 2.5 to 3 times per day. As soon as a cow enters position, the system scans its smart tag to retrieve health records and dispenses the exact amount of concentrated feed tailored to that individual. Notably, the robot is capable of real-time quality control. Sensors continuously analyze parameters ranging from electrical conductivity and fat content to somatic cell counts. At the slightest sign of mastitis or any indicator falling outside standards, a diversion valve immediately redirects the compromised milk into a separate tank without any human intervention. At the end of the process, the milking cups automatically detach and retract to a standby position, never touching the floor to ensure hygiene. The milk that meets standards then flows directly through a rapid cooling system to below 4 degrees Celsius before entering the main refrigerated storage tank. This entire journey takes place in a closed system, preventing any contact with air or bacteria. Beyond boosting milk yield by an additional 15%, this robot redefines livestock farming as a smart production line where humans manage data while cows are free to live according to their natural biological rhythms. Today, high-tech greenhouses can be found almost everywhere, but the density and scale in the Netherlands remain in a class of their own. Here, more than 9,000 greenhouses with a total area of up to 10,000 hectares are not crude plastic structures like those in Spain, but complexes of tempered glass operated by combined heat and power systems. By using natural gas to generate electricity for LED lighting arrays, then recovering waste heat for heating, these systems maintain a stable growth cycle 24/7, producing light so intense it can be clearly detected by satellites at night. There is an intriguing paradox. While the world struggles with emissions, Dutch farmers actually purchase industrial CO2 as fertilizer. Through a massive national pipeline network, excess CO2 is transported directly from refineries at the port of Rotterdam straight to the roots of plants inside greenhouses. After being injected through ultrafine piping systems, this CO2 allows plants to photosynthesize at extreme levels, accelerating growth cycles and increasing yields by up to 30% without expanding cultivated land. The pinnacle of this optimization is tomatoes, the #1 crop in Dutch greenhouses, with total production nearing 1 million tons per year. Despite the modest land area, export value still reaches $2 billion USD, making the country the world's second largest tomato exporter. Their strength lies in ultra-intensive cultivation. A single tomato plant can be harvested continuously for up to 11 months, thanks to hanging systems over 10 meters high and root systems neatly contained in inert growing media. This creates a stable, year-round production cycle, something that outdoor agricultural systems in Southern Europe or North America simply cannot sustain. Covering more than 40 hectares in just 1 hour, a level of productivity that once required an entire fleet of tractors. Equipped with high-precision GPS and multispectral sensors, they map the terrain, analyze moisture, slope, and canopy density, and calculate the optimal drop point for every grain. As the wind shifts, they automatically adjust their flight to ensure each seed falls with centimeter-level precision. Even in turbulent skies, radar and self-correcting algorithms keep them steady, quietly sowing the future of intelligent agriculture. After completing their mission of sowing life, these drones take on another role. As the aerial pharmacists of modern agriculture, carrying dozens of liters of crop protection solutions, foliar fertilizers or biological agents, they glide precisely over rows of crops, coating every leaf in a fine. Seeding drones represent the beginning of life. Spraying drones are its invisible shield, a symbol of an agriculture where artificial intelligence and flight technology are reshaping how humanity nurtures the earth. Mist. The fascinating machine before you, with its rotating steel blades cutting into the soil, may look like a set of lifeless metal arms, but in reality, it's the in-row weeder, an intelligent weeding system widely used by farmers across Europe and North America on high-tech vegetable fields. Each rotary blade is a curved steel tine mounted on a high-speed rotating shaft. As the machine moves, these shafts spin in perfect rhythm, allowing the tines to slip between plants, loosening soil, uprooting weeds, and breaking crusts, then retracting instantly before touching the delicate stems. Every motion is controlled by sensors, cameras, and precise electro-hydraulic systems, enabling the machine to detect the tiny gaps between plants with millimeter-level accuracy, as if guided by the intuition of a seasoned grower. With the ability to clear over 2 hectares per hour without a drop of herbicide, the in-row weeder not only replaces human labor but also paves the way for sustainable agriculture. where soil is cared for by machinery instead of chemicals. With the rotary rake, the idea behind its invention was simple yet brilliant. What if we could gather an entire field of grass with the precision of a Swiss watch? Unlike traditional rakes that drag along the ground, the rotary rake stands its rotors upright, allowing each flexible spring tine to gently lift the grass, spin it in a spiral motion, and form perfectly uniform windrows, as if measured by a ruler. The result? Grass that dries faster, stays cleaner, and retains up to 30% more nutritional value. Beneath its steel frame lies a network of self-balancing sensors and hydraulic controls, enabling the machine to cover over 12 hectares per hour while maintaining smooth, precise, and almost silent motion. Yet while the rotary rake brought finesse in keeping the forage clean and nutrient-rich, it quickly revealed its limits on the vast, sun-baked fields stretching hundreds of hectares. Slow speed, complex drivetrains, and limited flexibility. That's where the wheel rake takes over. A machine equipped with up to 20 steel wheels, spanning 12 meters in a single pass, creating a revolution in speed and efficiency. Without motors or drive shafts, the wheel rake harnesses the ground's own friction to convert motion into powerful sweeping force, flinging grass and hay neatly into straight, even windrows, as if drawn by a line. In this design, simplicity is strength. Fewer parts, lighter weight, and up to 20% less fuel consumption. The result? Nearly double the working speed, while maintaining the same stability and precision across every row. In modern livestock farming, industrial chicken production was once considered the optimal formula for cost efficiency and output. But as consumers began weighing animal welfare more seriously, free-range farming quickly emerged as a more progressive and hard-to-ignore alternative. In 2024, the global free-range chicken market was valued at around $17.4 billion and is projected to grow several times over in the next decade. Each year, the shift toward free-range systems increases by roughly 8%, especially in the UK and Australia, where free-range eggs account for nearly half of the commercial egg market. However, free-range doesn't always mean true freedom. In the United States, even a small door opened for a few minutes a day can be enough to legally qualify as free-range. But under the European animal welfare standards, only farms that provide at least 4 meters squared of outdoor space per chicken, with vegetation, sunlight, and real opportunities to forage, dust bathe, stretch their wings, and express natural behaviors, are recognized as genuinely free-range. And now to see whether free-range farming truly lives up to expectations, let's head to Australia, where the model is applied rigorously, making it one of the largest free-range markets in the world. The process of selecting and incubating eggs is a crucial stage that directly determines the health and productivity of the entire flock. The eggs are not chosen at random. They come from parent stock flocks carefully selected for breed quality, reproductive performance, and genetic traits. Meanwhile, in closed housing, staff prepare the floor with compressed wood shavings or treated soft wood chips. These materials retain heat well, naturally absorb moisture, and provide a soft cushion to protect the eggs while limiting bacterial growth. Here, the entire area is disinfected, sealed, and controlled for temperature, humidity, ventilation, and lighting. The cleaner the environment, the fewer pathogens have the chance to threaten the chicks. Unlike industrial incubation, free-range farms spread the eggs directly onto the barn floor. This method not only reduces stress and embryo mortality, but also helps chicks develop natural responses to heat, light, and humidity from the very first day. An eggshell is only about 3 times thicker than a human hair, yet contains up to 7,000 tiny pores. This means even slight pressure or vibration can damage the cuticle layer and allow bacteria to enter. That's why specialized egg-spreading equipment is used, featuring silicone suction heads and low vacuum pressure, strong enough to hold the eggs, but gentle enough not to deform the shell. The eggs are then placed onto a bed of wood shavings adjusted to the right warmth, with humidity maintained at around 55%, closely mimicking the natural conditions under a brooding hen. After about 18 to 19 days of incubation, the chicks begin to stir and pierce the air cell, a sign that the hatching process has officially begun. When ready, they activate their remarkable instinct to break free, pecking from the inside along a curved line, rotating their bodies clockwise while using the neck muscles to apply steady pressure. Each rhythmic peck gradually opens the shell's edge, like a pre-programmed escape mechanism. By this stage, the chick's respiratory system is fully developed, allowing it to supply its own oxygen and sustain the effort needed for the final push. Once the crack forms a full circle around the shell, the chick gives one last burst of force to pop the cap open and wriggle its way out, a small but decisive challenge for its survival. During the first 7 to 10 days after hatching, chicks must be kept in a closed brooding pen with dry bedding, stable heat lamps, and an automatic watering system. Faced to nipple drinkers, they quickly learn to drink on their own within a few days, significantly reducing the risk of digestive infections. At this stage, their diet consists mainly of crumbled starter feed, a formula with protein raised to about 20% to support muscle and skeletal development. The goal isn't to make them grow as fast as possible, but to build the basics, learning to find their own food, seek water, and adapt to flock behavior, rather than relying entirely on human caretakers. In Australia today, mobile chicken coops are spreading rapidly, especially across free-range farms and regenerative agriculture systems. Because they can be moved continuously across pasture, mobile coops reduce parasite pressure by up to 80% and improve soil organic matter after each grazing cycle. Many farms in Victoria and Western Australia even integrate solar panels, ventilation fans, and automatic doors to streamline operation. By combining animal welfare, soil improvement, and economic efficiency, mobile coops have become one of the fastest-growing models in the free-range poultry sector. And from this very moment onward, the defining privilege that sets free-range chickens apart from industrial birds truly begins. In fixed free-range systems, chickens are released outdoors according to a tightly controlled schedule. During the first few weeks, they spend only 2 to 3 hours outside each day to get familiar with the weather, the ground, and to learn how to return to the coop on their own. Once they adapt, outdoor time is extended to about 8 hours, usually from morning until late afternoon. Bringing them back to the coop each day helps maintain their natural rhythm. Supplemental feeding, rest, protection from cold night winds, and reduced exposure to predators. Although they forage freely, natural food sources supply only about 30 to 40% of their daily nutritional needs, so farmers must provide additional grains and minerals to ensure steady growth. Thanks to constant movement in an open environment, their metabolism accelerates. Subcutaneous fat decreases by roughly 30%, while thigh and breast muscles develop more prominently. As a result, their meat becomes firm, dense, and naturally springy, a texture that industrial farming cannot replicate, even with the same breed. By the 6th month, the hens begin laying eggs, and farmers collect each batch and transport it directly to the processing plant for packaging or for producing egg-based products. Each year, the world produces over 1.6 trillion commercial eggs. All of them are transported in the familiar trays, with cone-shaped hollows, triangular walls, and breathable surfaces. This seemingly simple design is highly effective. It locks each egg in place and reduces impact-related damage by up to 90%. From there, robotic arms equipped with force sensors and vacuum grippers lift entire stacks of trays without putting pressure on the shell surface. They rotate, raise, and place each stack onto the conveyor with precision, lining them up neatly and ready for the next stage of processing. Next, the eggs pass through an automated washing and sanitizing system. Low-pressure water is sprayed with just enough force to remove dust, manure, and straw debris without scratching the shell or damaging the natural cuticle layer. After cleaning, the eggs move into the candling chamber where high-intensity light, about 30 times brighter than a standard lamp, together with optical sensors, scans through the calcium shell to detect cracks, displaced air cells, faulty embryos, or traces of blood. Next, the eggs move through the solenoid unit. Each piston delivers a precise push to direct the egg onto the correct conveyor based on its size or any detected defects. After passing all inspection and grading stages, the eggs are moved to the packaging area. Here, robotic arms gently place each egg into molded pulp or plastic trays, keeping them stable and minimizing impact. Each tray is automatically labeled with detailed information: packing date, farm origin, egg type, and quality grade. The trays are then stacked into large cartons and sent into a cooling system to maintain freshness throughout transport. Refrigerated trucks collect the finished batches and deliver them to logistics centers, from where they are distributed to hundreds of supermarkets and retail stores. That is the process inside an egg processing plant. But what about free-range chicken meat? A product with higher nutrient density and a price often several times higher than industrial chicken. Free-range chickens are typically raised for 2 to 3 times longer than industrial birds, which gives them firmer muscles, stronger bones, and thicker connective tissue. As a result, several steps in the processing plant, such as stunning, plucking, and deboning, must be adjusted in force, timing, or temperature to handle the characteristics of this type of chicken properly. After the carcass is rinsed, the viscera extraction system removes the entire set of internal organs in a single motion, keeping the membrane intact to prevent leakage and reduce the risk of cross-contamination. As the bird moves through the giblets collecting station, the heart, liver, and gizzard are retained if they pass hygiene inspection, while the remaining parts are sent to the byproduct processing line. Next, the cropper machine removes the crop and esophagus, areas prone to food residue and microbial buildup, before the chicken moves on to the net cutting stage, carried out according to commercial standards. After being thoroughly rinsed, the chicken moves into the auto cut-up system, where clusters of automated blades cut with anatomical precision, dividing the meat into commercial portions such as whole birds, thighs, wings, breasts, necks, skin, bones, or organ parts. Depending on factors such as weight, muscle thickness, meat color, and intended use, all evaluated automatically, breast meat may be directed toward quick processing lines or premium products, while the skin, bones, and cartilage are utilized to produce collagen, meat powder, functional foods, or raw materials for the livestock industry. Free-range chicken typically has a richer, firmer flavor than industrial chicken, and its taste is somewhat similar to turkey, but lighter and more delicate. It is naturally high in protein, selenium, and vitamin B12, a good choice for those who prefer healthy eating. It can be cooked in many ways: roasted whole, pan-seared, or marinated with barbecue or Asian-style sauces. In terms of price, in Australia, a whole free-range chicken usually sells for around Australian dollars 19.50 at retail, while an equivalent industrial chicken may cost only about $8 to $10 per kilogram, meaning free-range chicken is nearly twice as expensive, depending on the region.